Welcome to the deep dive. I'm really glad you are pulling up a chair to join this conversation today because the stack of sources we are analyzing it's going to demand your complete intellectual attention.
Oh, absolutely. It is a really intense collection of documents today.
Yeah, it really is. We are looking at this highly curated and deeply interconnected collection. I mean, we have historical engineering notes from post-Napoleonic France. We have translations of these really complex 19th century German scientific treatises.
Right, and we also have some incredibly poignant, strictly documented biographical records to go with all that math.
Exactly. And the overarching mission today, for you listening and for us, is to take all of these disparate texts and trace the evolution of a single notoriously misunderstood concept in physics.
Entropy.
Entropy. Right, but by mapping out this specific historical timeline, we are actually attempting to expose a really profound and often uncomfortable truth about the nature of the scientific method itself.
Yeah, the epistemological stakes in these sources are just incredibly high. The central tension that runs through every single document we are going to look at today revolves around this massive, often unacknowledged gap in theoretical physics.
And it is a gap that I think a lot of people don't even realize exists.
No, they don't. We are exploring the chasm between finding a mathematical formula that perfectly flawlessly yields the correct empirical answer
Right.
and formally proving that it is the only mathematical formula that could possibly work.
Yes, the fundamental necessity of it.
Exactly. It is the distinction between discovering a highly functional mathematical model that just happens to map onto reality and proving the absolute logical necessity of that specific model.
And to really grapple with that gap, we need to trace the lineage of the concept from its physical origins to its eventual statistical abstraction. The notes map out this incredible 80-year arc.
It really is a wild journey.
It starts in 1824, and we are examining this largely forgotten treatise on the thermodynamics of steam engines, written by a really young French military engineer.
Sadi Carnot.
Right, and the timeline concludes roughly 8 decades later looking at a specific logarithmic equation carved into a marble tombstone in a Viennese cemetery.
And the journey between those 2 points is just fraught with fierce mathematical debates and philosophical crises and personal tragedy.
So let's begin by grounding the physics in its historical reality. We are in Paris, 1824, and we are introduced to Sadi Carnot. He is a 28-year-old military engineer trained at the highly prestigious École Polytechnique.
Right.
And he self-publishes a book. It is titled Réflexions sur la puissance motrice du feu. Reflections on the motive power of fire.
Which is such a poetic title for an engineering manual, but the geopolitical and industrial context surrounding Carnot's publication is it is essential for understanding his motivations here.
Because of what is happening across the channel.
Exactly. This is the era immediately following the fall of Napoleon's empire. So France is attempting to rebuild its geopolitical standing, while right across the English Channel, Britain is actively constructing this massive global empire.
And they are doing it almost entirely on the back of steam power.
Yes. The British have deployed steam engines to pump water out of deep coal mines. They're using them to drive the looms in their textile mills. They're even beginning to haul freight on iron rails. I mean, steam is the undisputed engine of the new global economy.
But the sources emphasize a really stark contradiction here. The British are masterful mechanics and engineers, but their theoretical understanding of thermodynamics is virtually non-existent.
They're just tinkering.
Right. They are tinkering. They understand the practical mechanics of boilers and pistons and pressure valves, but the fundamental physics governing the conversion of heat into mechanical work is just a total mystery to them.
And consequently, these early engines are operating at absolutely abysmal efficiencies. I mean, they're converting perhaps 3 to 5% of the thermal energy generated by burning coal into actual useful mechanical work.
3 to 5%. That is wild.
Yeah. The rest of that heat is simply lost to the environment. It is entirely wasted.
So Carnot looks at this and poses a theoretical question that essentially shifts the entire paradigm. He asks, is this catastrophic inefficiency simply a product of immature engineering that we can just, iteratively improve upon? Or is there a fundamental, insurmountable limit baked into the laws of nature regarding how much useful work you can extract from a heat source?
And to answer that question, Carnot does something really brilliant. He eschews the purely mechanical approach entirely.
Right, he doesn't go into a workshop to machine a tighter piston.
No, or design a larger boiler. Instead, he develops an epistemological tool. He invents an idealized thought experiment. He designs what physicists now refer to as the Carnot cycle.
Let's break that down for the listener because it is so foundational.
Okay, so he envisions a perfectly idealized, perfectly reversible thermal engine, and it operates through a specific four-stroke cycle.
And these are highly specific strokes.
Very. Two of the strokes involve the engine exchanging heat with a hot source and a cold sink isothermally.
Meaning the temperature remains constant during that specific exchange.
Exactly. The temperature is constant, and then the other two strokes involve the engine expanding or compressing adiabatically.
Which means there's absolutely no heat exchange with the outside environment during those specific mechanical movements.
Right. It is completely insulated. Now, the genius of isolating these variables in a thought experiment is that it allows Carnot to strip away the messy realities of friction and heat dissipation that plague real-world engineering.
He creates a mathematically pure environment to just observe the underlying dynamics.
Yes, and the revolutionary insight he extracts from this idealized cycle is that the absolute maximum possible efficiency of this perfect engine depends on one and only one variable.
Just one.
Just one. It relies entirely on the temperature differential between the hot source where the heat is entering the system and the cold sink where the exhaust heat is rejected.
And the mathematical formulation he eventually arrives at is incredibly elegant in its simplicity. The maximum theoretical efficiency equals 1 minus the ratio of the cold temperature to the hot temperature, measured on an absolute scale.
And when you abstract that formula away from the specific mechanics of 19th century steam power, the broader physical implications are just staggering.
Because it proves that the working fluid is irrelevant.
Completely irrelevant. Carnot mathematically demonstrated that the fluid inside the engine has no bearing on the ultimate theoretical efficiency. It does not matter if you use water vapor or atmospheric air or alcohol.
Or some hypothetical, highly advanced synthetic fluid that engineers might invent 3 centuries from now.
Exactly. It also does not matter how precise your machining is or how clever your valve timing might be. The absolute ceiling on your thermal efficiency is dictated entirely by the macroscopic temperatures you are operating between.
Which introduces a really profound concept to the scientific worldview.
Yeah.
Humanity is suddenly confronted with a hard universal constraint imposed by the laws of physics.
You cannot out-engineer the universe.
Right. If your hot reservoir is operating at, say, 1,000 degrees Kelvin, and your cold reservoir is at 300 degrees Kelvin, your absolute maximum theoretical efficiency is capped at roughly 70%.
That remaining 30% of the energy is inextricably lost.
And it is not lost because of a flaw in the design. It is lost because the universe fundamentally requires it to be rejected into the cold sink to complete the cycle.
It is the first time in the history of science that humanity stumbles upon a universal, inescapable boundary condition hiding inside the practical physics of industrial machinery.
However, there is a huge caveat here. Carnot was working under a theoretical framework that we now know to be completely incorrect.
Yes, he was. He was an adherent of the caloric theory of heat.
Right, which posited that heat was a weightless, invisible fluid called caloric that physically flowed from hot bodies to cold bodies.
Almost like water flowing over a water wheel to produce work. He believed that the total amount of caloric was strictly conserved throughout the engine cycle.
Which makes the historical trajectory of his work even more fascinating.
Yeah.
Because he derives a perfectly correct mathematical relationship regarding efficiency, but he derives it using a fundamentally flawed ontological model of what heat actually is.
It is a brilliant deduction from a false premise. But the immediate tragedy of Sadi Carnot isn't his adherence to the caloric theory.
No, it is the complete lack of contemporary recognition.
Right. He self-publishes his treatise, and it is met with profound silence from the scientific establishment. The notes indicate that between 1824 and 1834, this monumental text was cited precisely twice in the academic literature.
2 times in a decade. And then in 1832, during a devastating cholera epidemic sweeping through Paris, Carnot contracts the disease and dies.
He was only 36.
And the tragedy is compounded by the medical protocols of the era. Because cholera was so virulent and so poorly understood, the standard practice was to incinerate or bury the personal effects of the victims to prevent further transmission.
So many of Carnot's private journals and unpublished manuscripts and theoretical notes were simply buried with him.
His published book effectively vanished from the scientific consciousness. Booksellers forgot they even had copies in stock.
The physical survival of the idea is incredibly tenuous at this point. It relies almost entirely on another French engineer, Émile Clapeyron.
In 1834, Clapeyron happens to read Carnot's forgotten text, and he actually recognizes its brilliance.
But Carnot had written largely in prose, trying to make the concepts accessible. Clapeyron takes those prose descriptions and formalizes them into rigorous mathematics.
He introduces the graphical pressure volume diagrams, right? The PV diagrams.
Yes, the exact same PV diagrams that every physics student still uses today to visualize thermodynamic cycles. Clapeyron's formalized commentary is eventually translated into German in the 1840s.
And this translation finally crosses the desk of a physicist who possesses the theoretical vision to realize what Carnot had actually uncovered.
Rudolf Clausius.
Clausius. He is a monumental figure in this timeline because he is tasked with reconciling a major theoretical crisis in physics during the 1850s.
Right, because on one hand, he has Carnot's brilliant work on the motive power of heat, which relies on the idea that heat acts like a fluid flowing downhill.
And on the other hand, he has the contemporary experimental work of James Prescott Joule.
Exactly. Joule has recently demonstrated definitively that heat and mechanical work are interchangeable. He proves that heat is not a conserved fluid.
It is a form of energy that can be created through friction and consumed through work.
So Clausius realizes that to save Carnot's mathematical insights regarding efficiency, he has to completely tear down and rebuild the fundamental axioms of thermodynamics.
And out of that theoretical reconstruction, Clausius formulates the two fundamental laws of thermodynamics. The first law, which was being synthesized by several scientists, concurrently formally establishes the conservation of energy.
Energy cannot be created or destroyed. It merely changes forms between heat and work and internal energy.
But it is the formulation of the second law that represents Clausius's true masterpiece, because it introduces a concept of asymmetry into a previously symmetric physical worldview.
Clausius articulates the second law by stating a seemingly obvious empirical fact. Heat cannot spontaneously and without external work being performed flow from a colder body to a hotter body.
The flow of thermal energy is fundamentally unidirectional.
Right. Now, while that aligns perfectly with everyday experience, we all know a hot cup of coffee left in a room will cool down.
And the room will not spontaneously freeze to boil the coffee.
Exactly. But the mathematical implications of formulating this into a physical law are profound. Clausius realizes that this unidirectional flow implies the existence of an entirely new, mathematically rigorously defined physical quantity.
The notes detail his mathematical formulation in 1865. Clausius is looking at the ratio of the heat exchanged by a system which we denote as Q to the absolute temperature at which that exchange occurs, denoted as T.
And he proves mathematically that for any reversible cycle, the integral of this ratio, the sum of all the tiny changes in heat divided by the temperature, or dq over T, always equals 0.
This is a critical mathematical diagnostic. It means that dq over T is an exact differential.
Yes, it describes a fundamental state function of the system, a property that depends only on the current state of the system, completely independent of the path the system took to arrive at that state.
And that is the crucial distinction, because heat itself is not a state function. It is highly dependent on the path taken.
Mechanical work is not a state function either, but by dividing the infinitesimal heat transfer by the absolute temperature, Clausius discovers a new property of nature that is just as fundamental as volume or pressure or internal energy.
And he needs a nomenclature for this newly discovered quantity. He wants a term that will integrate seamlessly into international scientific literature alongside words like energy.
So he looks to the ancient Greek word propy, which translates roughly to transformation or turning, and he modifies it to create the term entropy.
He introduces the term, and then he delivers what the historical sources characterize as one of the most sweeping, audacious summaries in the history of theoretical physics.
It really is epic. He condenses the entirety of his thermodynamic framework into 2 stark sentences.
The energy of the universe is constant. The entropy of the universe tends toward a maximum.
The scope of that statement is breathtaking. By asserting that the entropy of the universe tends toward a maximum, Clausius inadvertently provides theoretical physics with an element it had been entirely lacking up to that point.
An arrow of time.
Yes, an arrow of time. Prior to Clausius, the foundational bedrock of physics was Newtonian mechanics. But Isaac Newton's laws of motion are perfectly time-symmetric.
Right. If you mathematically describe the trajectory of planets orbiting a star or billiard balls colliding on a frictionless table, the equations work perfectly, regardless of whether the time variable is moving forward or backward.
If you film a purely mechanical interaction and play the film in reverse, the reversed motion does not violate any Newtonian laws. Pure mechanics is completely blind to the direction of time.
which stands in stark contrast to our lived macroscopic reality. In the real world, phenomena are fundamentally irreversible. If you shatter a glass, the shards do not spontaneously reassemble themselves and jump back onto the table.
If you dissolve sugar in water, the water does not spontaneously expel the sugar crystals. Entropy provides the mathematical justification for this macroscopic irreversibility.
It acts as the ultimate physical arrow of time, because it dictates that the universe possesses a preferred unidirectional trajectory. It is moving relentlessly from states of lower entropy toward a state of maximum entropy.
And his contemporaries immediately grasped the cosmological implications of this law. Lord Kelvin extrapolated Clausius's second law to its ultimate chilling conclusion.
The heat death.
The heat death. If the entropy of the universe is constantly inexorably increasing, it means that all temperature differentials in the cosmos are slowly being smoothed out.
Eventually, after an unimaginable span of time, all matter and energy in the universe will reach a state of uniform thermal equilibrium.
There will be no hot stars and cold vacuums. Everything will be the exact same temperature.
And because, as Carnot proved, work can only be extracted when there is a temperature difference, no mechanical work will be possible in this state.
No engines can run, no chemical reactions can occur, no biological life can be sustained. Kelvin termed this the heat death of the universe.
It is a profound, almost terrifying cosmological vision derived entirely from the study of 19th century steam engines. But as we transition to the next phase of the timeline, the sources emphasize a critical epistemological limitation of Clausius's work.
By 1865, physics possesses an incredibly precise operational definition of entropy. They know exactly how to measure it using thermometers and calorimeters. They have the mathematical equations to track its increase.
They know what entropy does.
Yeah.
It governs efficiency limits and dictates the irreversible arrow of time.
But they have absolutely no theoretical understanding of why it does this.
Right. The second law is treated as an empirical axiom, an observed fact of nature that simply must be accepted. It is a highly effective macroscopic bookkeeping tool, but it offers no microscopic mechanism.
Which perfectly sets the stage for Act 2 of our timeline. And the introduction of a physicist who refuses to accept that's just the way nature is as an adequate scientific explanation.
We are looking at the work of the Austrian physicist Ludwig Boltzmann, born in Vienna in 1844. Which notably is the exact same year Sadi Carnot's foundational text was published.
Boltzmann comes of age scientifically in an era where thermodynamics is an established, rigorously codified branch of physics. But he is entirely unsatisfied with purely macroscopic operational descriptions.
He wants to understand the foundational underlying mechanics that give rise to the phenomena Clausius described.
And to do that, he proposes a theoretical framework that is so radical and so mathematically audacious that it fundamentally fractures the scientific community of his time.
Boltzmann makes the claim that entropy has absolutely nothing to do with the continuous flow of heat or macroscopic thermal fluids.
He posits that entropy is fundamentally a measure of combinatorial probability.
He argues that it is about counting the possible microscopic arrangements of discrete particles.
To appreciate the magnitude of this paradigm shift, we have to understand the conceptual architecture Boltzmann is proposing. He is demanding that physicists split their understanding of reality into two distinct mathematically connected layers.
The macrostate and the microstate.
Exactly. The macrostate represents the properties of a system that a human observer or an instrument can actually measure. Things like the overall temperature, the pressure against the walls of a container, the total volume of a gas.
It is the average bulk behavior of the system.
Right. But the microstate represents the hidden underlying reality. If you have a liter of gas in a sealed glass box, the microstate is the exact specific three-dimensional spatial coordinate and the precise velocity vector of every single individual gas molecule inside that box at one specific frozen instant in time.
It is an incomprehensibly vast amount of hidden data.
It is, and the foundational premise of statistical mechanics is linking these two layers. A single observable macrostate can be realized by an enormous number of different, constantly shifting microstates.
To illustrate how this statistical approach actually generates the phenomenon we call entropy, the sources suggest analyzing the permutations of a standard deck of 52 playing cards. And this analogy is incredibly powerful if we pursue the mathematics rigorously.
Let's do that. Imagine we break the shrink wrap on a brand new factory-sealed deck of cards. The cards are in perfect sequential order. All the spades from ace to king, then the diamonds, the clubs, and the hearts.
That specific, highly ordered sequence is our macrostate.
Now we ask the statistical question, how many specific arrangements, how many underlying microstates correspond to this exact perfectly ordered macrostate?
The answer is precisely 1. There is only one exact sequence of cards that satisfies the condition of being in factory order. The mathematical multiplicity of that macrostate is 1.
But the moment we begin to shuffle the deck, we are exploring the phase space of all possible permutations. The total number of ways to arrange 52 distinct cards is calculated as 52 factorial.
That is 50, 2 times 51 times 50, all the way down to 1. When you compute that number, you get a value of roughly 8 times 10 to the 67th power.
That is an 8 followed by 67 zeros. To contextualize the sheer scale of that phase space, if you were to shuffle a deck of cards thoroughly, the specific random-looking sequence you produce has almost certainly never existed before in the history of humanity and will almost certainly never exist again.
The number of possible microstates is so astronomically vast that if every human being on Earth shuffled a deck of cards once a second, every second, for the entire 13.8 billion year history of the universe, we would not even scratch the surface of exploring all 8 times 10 to the 67th possible arrangements.
And this staggering combinatorial math forms the bedrock of Boltzmann's brilliant physical intuition. When you shuffle that brand new ordered deck, the cards do not end up in a randomized disordered sequence because some mysterious physical force of disorder is actively pushing them away from their starting positions.
Right. They end up disordered simply because out of the 8 times 10 to the 67th possible arrangements, exactly one of them is the sorted state. And 8 times 10 to the 67th minus one of them are various unsorted, mixed-up states.
The transition from order to disorder is driven entirely by overwhelming probabilistic weight.
So applying this directly to the thermodynamics of a gas, imagine a sealed box divided by a barrier. On the left side, you have a mole of gas. On the right side, a vacuum.
This is a highly ordered, low-entropy macrostate. The gas molecules are constrained to a very small volume of the available phase space. There are a specific number of microstates, positions, and velocities available to them in that confined space.
Now you remove the barrier, the gas spontaneously expands to fill the entire box.
Clausius would say this happens because entropy must increase, but Boltzmann says it happens because the volume of the box has doubled, which means the number of available spatial coordinates for every single molecule has doubled.
The number of possible microstates available to the gas in the full box is incomprehensibly larger than the number of microstates available when it was confined to half the box.
The gas doesn't expand because the molecules have an inherent desire to fill the space, or because they are forcefully repelling each other into the corners.
It expands simply because, as the molecules move and collide randomly, they're exploring the available phase space. And the overwhelming dominating majority of that phase space consists of microstates, where the molecules are distributed relatively evenly throughout the entire volume.
The gas fills the room because an evenly distributed macrostate is supported by vastly more microstates than a clustered macrostate. It is statistically inevitable.
Boltzmann formalized this relationship in 1877 with an equation that represents one of the most significant intellectual achievements in physics. It is usually written as S equals K log W.
Let's unpack those variables. S represents the macroscopic thermodynamic entropy as defined by Clausius. W, from the German Wahrscheinlichkeit, meaning probability, represents the number of microscopic arrangements, the number of microstates that correspond to the observed macrostate.
And K is a proportionality constant now universally known as Boltzmann's constant, which scales the microscopic counting up to macroscopic measurable units.
The mathematical structure of this equation is deeply intentional, particularly the use of the logarithmic function.
Why did Boltzmann use a log?
Because he needed to reconcile two fundamentally different mathematical behaviors. In the macroscopic world of thermodynamics, entropy is an extensive additive property.
Right. If you have two separate boxes of gas, each with an entropy of 5, the total combined entropy of the system is 10. You just add them together.
But in the microscopic world of probability, the total number of combined microstates is multiplicative. If box A has W1 arrangements and box B has W2 arrangements, the total number of combinations is W1 multiplied by W2.
And the logarithm is the unique mathematical operator that transforms a multiplicative relationship into an additive one. The log of W1 times W2 equals the log of W1 plus the log of W2.
The mathematics perfectly bridges the microscopic and macroscopic realms.
But the philosophical implications of this mathematical bridge were deeply unsettling to the physics establishment.
Oh, absolutely. By defining entropy as a logarithmic measure of probability, Boltzmann inherently demoted the second law of thermodynamics.
Under the classical framework of Clausius, the second law was an absolute, deterministic, inviolable law of nature. Heat never flows from cold to hot. Entropy always increases.
But under Boltzmann's statistical mechanics, the second law is no longer an absolute axiom. It is merely a statistical likelihood of overwhelming magnitude.
Which means that, strictly speaking, temporary violations of the second law are not mathematically impossible. They are just incredibly improbable.
The equations allow for the possibility that all the oxygen molecules in the room you are currently sitting in could entirely by chance collide in such a specific coordinated sequence that they all gather in the upper left corner of the ceiling, leaving you to suffocate in a localized vacuum.
The mechanics do not forbid it. The probability of it happening is simply so infinitesimally small that you could wait 1 trillion lifespans of the universe and never observe it.
But mathematically, the absolute certainty of classical thermodynamics had been replaced by statistical fluctuations.
Furthermore, when Boltzmann ran his statistical calculations for ideal gases, his formula S equals klogW perfectly and flawlessly reproduced the exact same thermodynamic results that Clausius had derived using purely macroscopic assumptions about heat flow.
The predictive output of the combinatorial model perfectly matched the empirical output of the thermal model.
Which brings us to the core epistemological crisis highlighted by our sources. We have a mathematical coincidence. The numbers match perfectly.
But does matching the numbers prove that the two underlying concepts are exactly the same thing? Does the fact that a statistical counting exercise yields the same result as a calorimetric heat measurement definitively prove that thermodynamic entropy is statistical entropy?
Boltzmann firmly believed it did. He argued that his statistical mechanics represented the true, fundamental microscopic reality governing thermodynamic behavior.
But the scientific community of the late 19th century was rigorously skeptical. They were not prepared to accept that an established, observable law of nature could be reduced to a mere counting exercise of invisible, hypothetical entities.
The pushback he received was not simply petty academic rivalry. It was comprised of highly sophisticated, devastatingly precise mathematical and philosophical critiques.
The sources outline 3 specific major objections leveled against Boltzmann's theory. These objections act as diagnostic stress tests, probing the vulnerabilities of his mathematical bridge.
Let's delve into Act 3 and examine these critiques in detail. Starting with the first major challenge, which arrived in 1876 from a fellow Austrian physicist, Joseph Loschmidt.
This is universally referred to as the reversibility objection, or the Imkehreinwand.
Loschmidt's critique targets a fundamental, seemingly unresolvable contradiction between the mechanics Boltzmann was using and the macroscopic law he was trying to derive.
Boltzmann's entire statistical framework is predicated on the assumption that gas molecules act like tiny billiard balls bouncing around in a box, and that their movements and collisions are strictly governed by classical Newtonian mechanics. Specifically, their trajectories are governed by Hamilton's equations of motion.
And as we discussed earlier regarding the arrow of time, Newtonian mechanics are strictly deterministic and perfectly time-symmetric.
Precisely. The underlying mechanics are time reversible. Loschmidt constructs a rigorous thought experiment. He says, imagine an isolated box of gas where the system is evolving from a highly ordered low-entropy state to a disordered high-entropy state.
The molecules are colliding, exchanging momentum, and spreading out. Entropy is increasing in accordance with the second law.
Now, Loschmidt says, imagine that at a specific instant, we possess a magical physical intervention that allows us to instantaneously and perfectly reverse the velocity vector of every single molecule in the box.
We don't change their positions. We just exactly reverse their momentum. We make them travel backward along the exact trajectory they just took.
Exactly. Because Newtonian mechanics are time-symmetric, the system must precisely retrace its entire prior evolution. The molecules will undergo all the exact same collisions in reverse order.
The gas will evolve from the disordered high-entropy state back into the highly ordered low-entropy state it started in.
And the entropy of this isolated system will steadily decrease in direct, flagrant violation of the second law of thermodynamics.
So Loschmidt is presenting a devastating logical paradox. He is asking Boltzmann, how can you possibly claim to derive a macroscopic law that possesses a strict unidirectional arrow of time? Entropy always increases if every single microscopic interaction you are using to build that law is mathematically symmetric and works perfectly well in either direction.
You cannot magically extract an asymmetric irreversible result from purely symmetric reversible foundational equations. The mathematics of Liouville's theorem actually formalize this. In the phase space that describes these microstates, the total volume of the phase space fluid must remain constant over time. Information is never lost in pure mechanics.
To circumvent Loschmidt's paradox, Boltzmann had to introduce an assumption into his collision equations, a concept known as the Stoßzahlenansatz, or the assumption of molecular chaos.
This is a crucial point in the notes.
What exactly does the Stoßzahlenansatz assume?
It essentially assumes that before any two molecules collide, their velocities are completely uncorrelated and statistically independent. It assumes the molecules have no memory of past collisions.
By inserting this assumption of continuous uncorrelated chaos, Boltzmann effectively severed the mathematical link to the past. He smuggled irreversibility into the equations by manually breaking the time symmetry through a statistical assumption.
But to his critics, including Loschmidt, this felt like a massive epistemological sleight of hand. They argued that Boltzmann hadn't actually derived the second law from pure mechanics. He had simply assumed the second law by injecting the Stoßzahlenansatz into the math.
When pressed on the existence of those time-reversed entropy-decreasing trajectories, Boltzmann had to retreat to probabilistic arguments.
He conceded that those trajectories technically exist in the phase space, but he argued they represent an infinitesimally small fraction of the total possible trajectories.
He argued that the universe must have simply started in an incredibly rare, highly ordered initial condition, and from that starting point, the vast, overwhelming majority of accessible paths lead to higher entropy.
While mathematically plausible, relying on highly specific initial conditions of the universe felt philosophically weak to his contemporaries. It didn't feel like a fundamental law of physics, it felt like a circumstantial excuse.
And this vulnerability was exploited even more rigorously 20 years later in 1896 with the second major critique, the recurrence objection presented by the mathematician Ernst Zermelo.
Zermelo attacks Boltzmann not with a thought experiment, but with a formal mathematical proof derived from topology and dynamical systems. He bases his critique on a theorem recently published by the brilliant French mathematician Henri Poincaré, known as the Poincaré recurrence theorem.
The recurrence theorem is a profound piece of mathematics. Poincaré proved that for any classical mechanical system enclosed in a finite spatial volume with a finite amount of total energy, such as a sealed box of gas, the system must eventually return to a state that is arbitrarily close to its initial starting state.
Because the system is bounded, the phase space it can explore is finite. It will evolve, it will change, but eventually the trajectories must loop back on themselves.
If we return to our deck of cards analogy, it essentially means that if you sit there and shuffle the deck randomly for a long enough period, the mechanics of shuffling guarantee that you will eventually, inevitably shuffle the cards back into perfect factory order.
Precisely. And Zermelo uses this mathematical certainty as a battering ram against Boltzmann's statistical second law.
Zermelo argues, if the underlying mechanics dictate that the gas must eventually return to its initial low entropy state, then the entropy of the system must eventually decrease to reach that state.
Therefore, you cannot define the second law of thermodynamics as an eternal unidirectional increase in entropy. The mathematics of recurrence strictly forbid it. The system is cyclical, not unidirectional.
The notes indicate that Boltzmann's response to Zermelo is fascinating because he doesn't dispute the mathematics.
He can't. The Poincaré theorem is rigorously proven. Instead, he disputes the physical relevance of the timeline. Boltzmann calculates the recurrence time, the amount of time you would actually have to wait for a macroscopic system to spontaneously return to its initial state.
And the calculation yields a number that defies human comprehension. Boltzmann determines that for a typical macroscopic volume, say a single mole of gas, which is roughly the number of atoms in a handful of matter, the time required for a Poincaré recurrence is on the order of 10 to the power of 10 to the 19th years.
Let's pause and genuinely grapple with the sheer scale of that number, because it is difficult to convey just how massive a double exponential is. 10 to the 19th is already a 10 followed by 19 zeros. It's an unimaginably huge number.
But the recurrence time is 10, raised to the power of that massive number. If you attempted to write out the recurrence time in standard notation as a 1 followed by zeros, you could write a 0 on every single atom in the observable universe, and you would run out of atoms long before you finish writing the number.
It makes the 13.8 billion year age of our universe look like a fleeting fraction of a millisecond.
Because the timeline is so absurdly vast, Boltzmann argues that Zermelo's objection is physically meaningless. He essentially tells Zermelo, yes, your mathematical theorem is technically correct, but the recurrence time is so incomprehensibly longer than any conceivable timeline of the universe that no observer will ever witness it.
For all practical physical purposes, the second law holds.
But again, we are looking at this through the lens of epistemology. From the perspective of pure mathematics and the philosophy of science, you are technically right, but it takes too long to matter, is a terribly unsatisfying defense.
It concedes that the second law is not a fundamental, immutable truth of nature, but merely a temporary, highly localized illusion caused by the limited timescale of human observation. It leaves the fundamental theoretical conflict unresolved.
Which brings us to the third and arguably the most dangerous objection Boltzmann faced. This critique did not arise from the mechanics of reversibility or the topology of recurrence. It arose from a fundamental debate about the very definition of scientific inquiry.
This is the positivist rejection championed by the highly influential physicist and philosopher Ernst Mach and the prominent physical chemist Wilhelm Ostwald.
Mach's philosophical stance, known as logical positivism or empirio-criticism, was a dominant intellectual force in late 19th century German-speaking science. And it's important to understand that Mach wasn't just being stubborn. Positivism was a highly rigorous, respectable attempt to purge physics of unsubstantiated metaphysical assumptions.
Mach argued that science must be strictly confined to describing and connecting observable, measurable phenomena. If a concept cannot be empirically verified through sensory experience or direct measurement, it has no place in a rigorous physical theory.
And this epistemological strictness posed an existential threat to Boltzmann's entire statistical framework, because in the 1890s, the atom was entirely hypothetical. No one had ever seen an atom.
No instrument was capable of detecting an individual molecule. They were theoretical constructs. Mach argued that building an elaborate, highly complex mathematical architecture on top of invisible, undetectable microscopic billiard balls was a regression into alchemy and metaphysics.
He famously demanded of atomists, have you seen one?
Wilhelm Ostwald took Mach's philosophical skepticism and attempted to build an entirely new atom-free physical paradigm out of it, a movement known as energetics.
Ostwald argued that instead of relying on hypothetical microscopic particles, physics should be entirely reconstructed using the one macroscopic quantity that was universally observable and measurable: energy.
He wanted to describe all chemical reactions, all thermodynamic behavior, and all physical phenomena purely in terms of continuous energy transformations, completely eliminating the need for a discontinuous atomic model of matter.
Ostwald's energetics program was highly appealing to many scientists because it felt theoretically clean. It didn't require assumptions about molecular chaos or invisible collisions. It relied solely on the established macroscopic laws of thermodynamics.
If energetics succeeded, it would render Boltzmann's entire life's work irrelevant. If matter is a continuous distribution of energy rather than discrete particles, then Boltzmann has absolutely nothing to count.
His combinatorial parameter, W, in the equation S equals K log W, becomes completely meaningless.
This philosophical friction between the atomists and the energeticists wasn't just confined to academic journals. It culminated in a highly dramatic public confrontation.
The sources point us to Act 4, the Lübeck debate. Let's set the stage for this because the sociology of late 19th century German science provides a fascinating backdrop. It is September 1895.
The setting is the Versammlung, the annual highly prestigious gathering of German scientists and physicians held that year in the city of Lübeck.
The structure of these conferences was generally quite formal and polite. Papers were circulated, formal responses were read, and disagreements were usually handled with a degree of detached collegial respect.
Wilhelm Ostwald and his colleague Georg Helm arrived in Lübeck expecting exactly this kind of gentlemanly reception. They were prepared to present their latest papers advancing the mathematical framework of energetics, anticipating a British-style discussion. Respectful give and take.
But the sources indicate they walked into an ambush. Ludwig Boltzmann was serving on the program committee for the Lübeck conference, and he deliberately arranged for dedicated sessions focusing on Ostwald's energetics.
But Boltzmann had not spent the preceding months merely preparing rhetorical arguments. He had been forensically analyzing the underlying mathematics of Ostwald and Helm's published papers.
He had found the foundational mathematical flaws in their continuous energy models.
During the session, Boltzmann systematically and ruthlessly dismantled the theoretical framework of energetics. He demonstrated live and in public that Ostwald's mathematics were internally inconsistent.
He proved that you cannot derive the complex necessary equations of motion for a physical system relying solely on scalar energy relations. You need vector quantities. You need a proper Lagrangian formulation, which the energetics framework completely lacked.
He exposed that attempting to describe complex physical dynamics without acknowledging a particulate structure leads to mathematical dead ends.
The archival notes contain a vivid eyewitness account of this confrontation from Arnold Sommerfeld, who was a young mathematician at the time, and who would eventually become one of the most important theoretical physicists of the 20th century.
Sommerfeld's description of the debate is legendary. He characterized it as a struggle between a supple fencer and a charging bull.
Ostwald was the fencer. Agile, rhetorical, philosophically eloquent, and highly charismatic.
But Boltzmann was the bull. He possessed a massive, undeniable physical presence and an absolute crushing command of the mathematics. And as Sommerfeld succinctly noted, the bull won.
The outcome of the Lübeck debate was a decisive victory for the atomists, at least in terms of mathematical rigor. Sommerfeld noted that the younger generation of mathematically inclined scientists in the audience was unanimously swayed to Boltzmann's side.
Even Felix Klein, who was arguably one of the most preeminent mathematicians in the world at that time, publicly expressed his support for Boltzmann's mathematical critique. Boltzmann successfully proved that energetics, as formulated by Ostwald, was a mathematically inadequate substitute for statistical mechanics.
However, the notes draw a critical distinction regarding the nuance of this victory. Winning the mathematical sparring match on the floor of the conference hall did not translate to winning the broader philosophical war.
The confrontation was deeply unpleasant for Ostwald and Helm, who felt they had been subjected to a hostile cross-examination rather than a scientific debate.
And more importantly, demolishing Ostwald's specific mathematical models did not neutralize Ernst Mach's overarching positivist objection.
Boltzmann proved that energetics was flawed, but that negative proof did not magically materialize empirical evidence for the existence of atoms.
Mach remained steadfast. Until an atom could be observed or measured, statistical mechanics remained a highly effective yet fundamentally unproven mathematical fiction.
Boltzmann was forced into a somewhat defensive, pragmatic epistemological corner. He had to argue that the atomic hypothesis was an incredibly useful predictive model or picture of reality, while simultaneously conceding that he could not definitively prove the model represented the absolute ontological truth of matter.
He had defended his equations, but he remained trapped in the gap between a model that works and a model that is proven to be necessary and true.
This unresolved tension transitions us into Act 5. Tragedy, irony, and the unresolved gap. The historical timeline following the Lübeck debate is characterized by agonizing irony.
The scientific vindication Boltzmann so desperately fought for begins to materialize almost immediately, but it arrives in ways he could not fully anticipate or utilize.
The first major irony involves Max Planck. Planck had historically been highly skeptical of Boltzmann's statistical approach, favoring the absolute certainty of Clausius's macroscopic thermodynamics.
However, by the winter of 1900, Planck is struggling to solve one of the most intractable problems in physics, the spectrum of black-body radiation.
Classical continuous physics was producing equations that predicted an ultraviolet catastrophe, an absurd result indicating that a black body should emit infinite energy at high frequencies.
To resolve this theoretical crisis, Planck describes taking an act of despair. He abandons his continuous models and reluctantly adopts Boltzmann's exact statistical counting methods.
To make the mathematics work, Planck introduces the radical idea that electromagnetic energy must be emitted and absorbed not continuously, but in discrete quantified packets, or quanta.
By applying Boltzmann's combinatorial techniques to these discrete energy packets, Planck successfully derives the correct law for blackbody radiation, inadvertently birthing the entire field of quantum mechanics.
And the final equation he produces relies intrinsically on a fundamental constant required to scale the statistical probability to macroscopic entropy.
That constant K is formally introduced to the world by Planck, but he names it Boltzmann's constant, acknowledging the profound debt his new quantum theory owes to Boltzmann's statistical framework.
The man who doubted this statistical method uses it to pry open the subatomic universe.
And the irony continues 5 years later. In 1905, during his miracle year, a 26-year-old patent clerk named Albert Einstein publishes a theoretical paper on a phenomenon known as Brownian motion.
Brownian motion refers to the erratic, random jittering movement of microscopic particles like pollen grains suspended in a fluid. It had been observed through microscopes for decades, but it lacked a rigorous physical explanation.
Einstein provides that explanation by deeply absorbing the implications of Boltzmann's atomic theory. Einstein argues mathematically that the visible macroscopic jittering of the pollen grain is not random. It is the direct statistical consequence of being constantly asymmetrically bombarded by the invisible microscopic water molecules surrounding it.
Einstein uses the statistical mechanics developed by Boltzmann to calculate the mean squared displacement of the pollen grain, providing a precise mathematical link between a visible macroscopic effect and invisible microscopic collisions.
It is the ultimate refutation of Mach's positivist critique. Einstein essentially proved that you don't need to see the atom directly, you can rigorously measure its physical impact on the macroscopic world.
It provided the exact empirical proof of discrete molecular reality that Boltzmann had spent his entire career demanding.
Tragically, Boltzmann would not live to see the scientific community fully digest and accept Einstein's proof, nor the experimental confirmations that followed.
This brings us to the personal history of Ludwig Boltzmann, which the sources instruct us to handle with rigorous nuance and extreme care. The historical record provides a portrait of a remarkably complex, deeply human figure.
He was not a detached, ascetic intellectual. He was a passionate musician who loved playing the piano. He was incredibly generous with his time and deeply beloved by his students, a roster that included brilliant minds like Lise Meitner, who would go on to co-discover nuclear fission.
He possessed a sharp, often self-deprecating wit. He frequently joked that his notoriously rapid shifts in temperament were a result of being born during the night between the revelry of Mardi Gras and the solemnity of Ash Wednesday.
But running parallel to that brilliance and warmth was a severe, rigorously documented medical reality. Boltzmann suffered profoundly from what modern psychiatry would almost certainly diagnose as severe bipolar disorder characterized by manic highs and absolutely crushing, paralyzing depressive episodes.
As he aged, these psychological struggles were compounded by physical ailments. His eyesight was rapidly deteriorating, severely impeding his ability to read and write mathematics. He suffered from chronic debilitating asthma and severe headaches.
Furthermore, he was plagued by a terrifying obsessive fear that he was losing his intellectual faculties and his memory.
It is critically important to emphasize this medical context because there is a pervasive romanticized myth in the history of science that reduces Boltzmann to a tragic martyr.
The myth suggests that he was a lone genius, bullied into suicide, by a dogmatic scientific establishment that callously rejected his ideas.
While the intense intellectual isolation and the brutal attritional nature of the theoretical debates with the energeticists undoubtedly caused him immense stress and exacerbated his condition, portraying his death solely as the result of a lost scientific argument does a profound disservice to the reality of severe clinical depression.
It reduces a complex medical tragedy to a neat, dramatic narrative trope.
The culmination of these intertwined struggles occurred on September 5, 1906. Boltzmann was on a late summer holiday with his family in Duino, a picturesque village on the Adriatic coast near Trieste.
While his wife Henriette and his daughter were away from the hotel swimming, Ludwig Boltzmann ended his own life. He was 62 years old.
It is a devastating, abrupt end to a life that had so profoundly reshaped human understanding of the physical world.
The deeply bittersweet coda to his personal narrative is located in the Central Cemetery of Vienna. His gravesite is marked by a marble bust, and carved into the stone above his head is the equation S equals K log W.
The ultimate irony of that tombstone is the notation. Boltzmann himself never wrote the equation in exactly that concise modern form.
The specific arrangement of those symbols, S equals K log W, was formalized by Max Planck. It was carved into the marble as a posthumous tribute by the physicist who had once been his sharpest critic, but who had ultimately realized that Boltzmann had discovered a fundamental, indispensable truth about the architecture of reality.
The tombstone is a powerful monument, but as our sources dictate, we must separate the emotional resonance of his life from the rigorous evaluation of his science. We need to execute an epistemological assessment.
Act 6 demands that we take a step back and objectively evaluate the status of Boltzmann's theoretical framework at the specific moment of his death in September 1906.
We need to run an analytical scorecard judging his work against the core theme we established at the beginning: the profound gap between formulating a mathematical model that generates the right answers and proving the fundamental logical necessity of that specific model.
Let's methodically run through the criteria of that epistemological scorecard. Criteria number 1, pattern recognition. Did Boltzmann's statistical framework successfully match the observed physical reality?
The assessment here is incredibly strong. The pattern matching was virtually flawless. Everywhere the equations were applied, Boltzmann's combinatorial formula perfectly reproduced the macroscopic thermodynamic results that Clausius had derived empirically. The statistical mechanics consistently yielded the correct thermodynamic values.
Criteria number 2, uniqueness. Was Boltzmann's specific logarithmic formulation the only mathematical model capable of producing these correct results?
This is where the profound gap becomes visible. The answer in 1906 was unknown. Boltzmann had demonstrated that his specific counting method worked brilliantly, but no one had systematically mathematically proven that S equals klogW was the unique, exclusive, and singular function capable of mapping probability to entropy.
It was highly effective, but its mathematical exclusivity remained unproven.
Which leads directly into criteria number 3, the bridge theorem. Did Boltzmann provide a rigorous logical proof of necessity linking the microscopic mechanics to the macroscopic law?
The verdict here is absent. Boltzmann constructed an incredibly sturdy mathematical bridge showing that counting microstates could reproduce macroscopic thermodynamics, provided one accepted certain statistical assumptions like the Stossel-Ansatz.
However, he did not provide a fundamental proof that the underlying laws of physics mathematically demanded that specific bridge and no other. He proved sufficiency it works, but he did not prove logical necessity.
Criteria number 4, novel prediction. Did his statistical framework predict any new observable physical phenomena that classical continuous thermodynamics could not?
The assessment is partial. Because his theory relied on statistical probabilities rather than absolute certainties, it inherently predicted the existence of fluctuations, tiny, localized deviations from perfect thermal equilibrium.
Einstein's 1905 paper on Brownian motion formalized the mathematics of these fluctuations, but the decisive, irrefutable experimental data confirming Einstein's math would not be published by the French physicist Jean Perrin until 1908, 2 years after Boltzmann's death.
So the theoretical prediction existed, but the experimental confirmation was pending.
Finally, criteria number 5, ontology. Did the physical entities described by the mathematics actually exist in reality?
Contested. At the exact moment of his death, the absolute physical reality of discrete atoms and molecules remained technically unproven to the satisfaction of the strict Machian positivists. They were still viewed by many as highly useful predictive heuristic devices rather than confirmed ontological facts.
Synthesizing the scorecard provides a clear, objective view of his legacy in 1906. Ludwig Boltzmann constructed a theoretical framework of overwhelming explanatory power, incredible elegance, and immense predictive utility. It was almost certainly correct in its broad strokes.
Yet, from a strictly logical and epistemological standpoint, it remained incomplete. He possessed the right mathematical answer, but he lacked the ultimate ironclad proof of fundamental necessity and unique exclusivity.
That is the unresolved tension that closes this chapter of the history of science. The vindication of the ontology, the definitive proof that atoms were real, was literally on the horizon.
Jean Perrin's meticulous experiments on colloidal suspensions in 1908 would provide the undeniable physical evidence required to confirm Einstein's mathematics of Brownian motion. The evidence was so overwhelming that even Wilhelm Ostwald, the fierce champion of continuous energetics, publicly conceded the discrete atomic nature of matter in 1909.
Boltzmann's physical intuition regarding the particulate nature of reality was absolutely vindicated.
However, the proof of the formula's mathematical necessity was not vindicated alongside the atoms. The profound logical gap between the thermal world of heat engines and the combinatorial world of statistical probabilities remained wide open.
Boltzmann proved that counting microstates generated the correct macroscopic answers, but the fundamental question of why the universe demanded that specific logarithmic relationship and whether any alternative mathematical formulations were possible remained entirely unanswered by the physicists of the early 20th century.
And what makes this historical narrative truly remarkable is the origin of that final missing piece of the puzzle. The rigorous mathematical proof demonstrating exactly why S equals klogW is the unique, necessary, and logically unavoidable formula for entropy does not emerge from the world of thermodynamics.
It is not discovered by a physicist staring at the pressure gauges of a steam engine, nor is it derived by someone calculating the collision trajectories of gas molecules in a theoretical box.
No, it represents a massive paradigm shift. The missing proof of fundamental necessity wouldn't arrive in the scientific literature for another 42 years after Boltzmann's death.
And it wouldn't come from a theoretical physicist. It would be derived by an electrical engineer working at Bell Laboratories. a researcher trying to solve a highly practical mid-20th century problem regarding how to accurately transmit digital telecommunications signals over noisy, interference-prone telephone lines in the year 1948.
But the specifics of that 1948 breakthrough and how telecommunications engineering finally closed the epistemological gap left by 19th century thermodynamics is an entirely different deep dive.
We're going to leave that historical connection completely suspended for now. You're going to have to sit with the discomfort of the unresolved gap. Boltzmann lived and struggled and died in that exact intellectual chasm, the space between achieving immense practical mathematical success and possessing absolute fundamental logical certainty.
Sitting with that specific tension is vital because it forces us to recognize that science is rarely a process of immediate absolute revelation. It is a slow, iterative, and often painful process of narrowing the gaps in our understanding.
I want to leave you with a final provocative thought to consider after we wrap up today. We have spent this time examining the history of a profound mathematical equation. But think about the architecture of your own daily life. Think about the technological tools, the economic rules, or the complex social systems you rely on every single day.
You know they function. The outputs match your expectations perfectly every time you interact with them.
But have you ever stopped to interrogate why they are structured the way they are? How much of your world, how much of our modern reality operates on a brilliant, highly functional coincidence that works beautifully in practice, but that nobody has actually proven the ultimate fundamental necessity of? Are you living your life relying on a right answer without ever questioning if it is the only answer?
That is the profound, unsettling question that drives the very heart of the scientific endeavor.
Thank you for bringing your curiosity to this deep dive. Until next time, keep interrogating the formulas that govern your world. Take care.